Let's take a look at the final review solution set for Chapter 5, which deals with the quadratic formula and imaginary and complex numbers. The quadratic formula is shown here, and we will remember that it is a formula and a model for expressing the zeros of a quadratic function. And the zeros of a quadratic function are the x-intercepts. We are essentially asking what values for x in a quadratic function will produce an output value of 0. So we can see here the values of x which make y equal to 0, or the x-intercepts of the parabola graph. So let's take a look. We have our quadratic formula, which is x equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. And once again, this is based on the standard form of a quadratic expression or a quadratic function, which is y equals ax squared plus bx plus c. And we are basically just setting that quadratic function equal to 0 and solving for the input values, the x values, that will create a value of 0 for the function. We can see here that we have expressed our coefficient values. Our a value is equal to -3, our b value is equal to +10, and our c value is equal to -3 as well. In the quadratic function, -3x squared plus 10x minus 3 equals 0. We have our a, b, and c values. We have our formula for the quadratic formula, and then it is a matter of being organized and following our order of operations and understanding the mathematical operations that are built into the formula itself. So we can see our steps here. The opposite of 10 plus or minus the square root of 10 squared minus 4 times -3 times -3 all over 2 times -3, as +10 is our b value, so that is expressed here and here. Our a value is -3, our c value is -3, and then in the denominator our a value is -3 as well. That creates -10 plus or minus the square root of 64 all over -6. Notice this plus or minus sign in front of the square root. Remember, that shows us that every square root value has a positive version and a negative version of itself, because a positive number squared can equal 64, and also a negative number times itself can also equal +64. And as we can see here, the square root of 64 is technically positive or -8. That is what creates our two zeros, the two x-intercepts of the parabola, because now we have basically two separate numerators for our quadratic formula when we get to this stage. So we have -10 plus 8 divided by -6, and we also have -10 minus 8 divided by -6. That produces two x-intercepts, or two zeros of the function. And those two values are 1/3 or +3. Either of those values, 1/3 or +3, when substituted back into the original function, would produce an output value of 0. That is what those two values represent. Moving on to imaginary numbers. If we remember, the basic model for an imaginary number is that I, the imaginary number, is equal to the square root of -1. This comes about when we have a basic situation like this. X squared equals -9. So we run into an issue when we try to take the square root of a negative number, because the square root of a number is essentially what number times itself equals that value. So if we're asking ourselves what value times itself equals -9, that goes against our understanding of multiplication. Because in order to multiply two values to get a negative value, such as -9, we understand that one would have to be positive and one would have to be negative. And that goes against the idea of something squared, because something squared is something times itself. So we have what is known as an imaginary number. And that imaginary number is I, and it is represented as the square root of -1. So when we have the square root of a negative number, based on our radical models, we know that we can split this value up into the square root of any of its factors. So we can take the square root of -9 and break it up into the square root of -1 times the square root of +9. And that process can take place with any square root of any negative number. We break it up into the square root of -1 times the square root of the positive version of that number, and then proceed to simplify the radical expression from there. So the square root of -1, as we stated, is represented as I, the imaginary number, and then the square root of 9 is 3. So in this case, x squared equals -9. When we take the square root of both sides, we are left with x equals 3i. And that is an imaginary number. Taking a look at the other examples, we solve for the variable in the same way that we solve for any variable using algebraic means. For this example here, 2x squared plus 3 equals -13. We would add or subtract terms away from the variable that we are solving for, in this case x, and when we do that, we are left with 2x squared equals -16. When we divide by +2 to isolate the variable, we are left with x squared equals -8. And again, we are in a position that when we take the square root of both sides, we are trying to find the square root of a negative number. Again, we can separate that square root of a negative number into the square root of -1 times the positive version of that number. Square root of -1 becomes I, and the square root of 8 gets broken up into the square root of 4 times the square root of 2. Remember, when we are simplifying radicals, it is in simplest form if it does not have any perfect square factors. So we are looking at the square root of 8 and asking ourselves, does 8 have any perfect square factors? It does, 4. The square root of 4 becomes 2, and the square root of 2 stays the square root of 2. That's in simplest radical form. And so we have our solution as x equals 2 times the imaginary number I times the square root of 2. We see that that process takes place in a very similar fashion for this example problem here. And I want to point out the example problem here on the left, which is the value of x minus 1 squared, that whole value squared, equals -7. Since x minus 1 is in parentheses, it is a single entity. We just do not know what that single value is. That is a single value being squared. So we can take the square root of that entire single value, and we can take the square root of -7 by taking the square root of both sides. Whatever we do to one side of the equation, we can do to the other. The square root of x minus 1 squared is simply x minus 1. The square root of anything squared is that value. The square root of -7 is simply 7i, or excuse me, the square root of 7 times I. The square root of 7 times the square root of -1 is how we can break this up. The square root of 7 stays the square root of 7 because it does not have any perfect square factors, and the square root of -1 becomes I. We can then solve for the variable by adding 1 to both sides. Again, our basic algebraic solve for a variable process, and we are left with the solution x equals 1 plus root 7 times I. Complex numbers are a combination of real numbers and imaginary numbers. When we are adding or subtracting complex numbers, we treat the variable I like we would any other variable in terms of combining like terms. So we can see here that when we are adding and subtracting complex numbers, we are treating the variable I like we would any other variable. This is 4 plus 3. This is where we get the real number 7 from. And we are essentially combining negative 1I. There's a negative 1 coefficient in front of this I like we would think about any other variable. Negative 1I plus 2I. So negative 1 plus 2, that is where we get positive 1I here from in terms of combining like terms, and we are left with 7 plus I. Once again, combining like terms, we have a positive 7 and a negative 1. When we distribute this negative 1 through the parentheses, that's where we get positive 6 from. And we have a negative 5, and we will have a positive 5 when we distribute this negative 1 through the parentheses here. So we'll have negative 5I plus 5I. That is where we get 0I from, and still 0 times I is 0, and we are left with simply just positive 6. The one rule, before we move on that I want to point out is that if the square root of negative 1 equals I, then we also learned that I squared must then equal negative 1. So I squared has a real value. The square root of negative 1 equals I, and I squared equals negative 1. That comes into play when we are now multiplying complex numbers. Take a look at our first example here on the left. 5I times the value of negative 2 plus I. We use our distributive property and distribute 5I through the parentheses. 5I times negative 2. Again, we treat this variable I like any other variable. This is 5 times negative 2 times I, which is negative 10I. Now, 5I times positive I is where we would get 5I squared from. We just reviewed that I squared has a real value, which is negative 1. So we can substitute negative 1 here for I squared. So instead of plus 5I squared, it's plus 5 times negative 1. Positive 5 times negative 1 is negative 5, and that is where we get the expression negative 10I minus 5, or more correctly, negative 5 minus 10I, as that is the model how complex numbers are written. A plus BI, the real number plus the imaginary value. Again, we have now two binomials. We reviewed earlier about the FOIL method or the distributive property twice when you are multiplying two binomials, and the same processes and rules apply. So we can FOIL these two values, and again, we are left with combining like terms. 14I plus 4I here in the middle produces 18I. But when we do our last step in the FOIL method, or the last process of the distributive property, we see that negative 4I times positive 2I yields negative 8I squared. And like the previous example, I squared has a real value, which is negative 1. So negative 8 times negative 1 is positive 8. That can then be combined with negative 7, combined like terms, and that is where we produce the final solution, 1 plus 18I, as the result of multiplying these two complex numbers.